Hello and welcome to the very first technical NCTV episode. If you have an interest in Foundry technology and casting simulation specifically, then this is for you. Our technical simulation manager Håkan will digitally demonstrate how to save time, resources and money by compensating your mold. So Håkan, what does mold compensation mean?
Mold compensation means that you are, instead of like you traditionally make, adding a percentage to the casting part in order to retrieve a mold cavity or a pattern, you are simulating this. So you are making a solidification simulation followed by a stress calculation, and from them you get the simulated dimensional changes and also the shape changes from the casting simulation then, and that you can then invert and use as the starting point for the pattern, and that means that you get more correct dimensions.
When would you say this is significantly helpful?
I would say it's helpful for all type of casting methods, but of course more where you have higher demands for accuracy, but you can use it for all types because you get better than the dimensions and also the shapes. Especially I would say it's interesting for high pressure die casting and investment casting, or lost wax as it is also called, because those methods are high accuracy methods and they need to have very good dimensions.
So the process is like this. The 3D model should be equal to the dimensions you want in the final casting. This is not as it is for normal simulations, because then we are using the cavity. The cavity is what we need to use as for the normal simulations, meaning that we have already added this percentage of dimensional changes for compensating the liquid contraction, the solid contraction, the solidification contraction, and the solid contraction. So that is what we need to do, but not for this simulation. Here you should use the final casting part as it should be sent to your customer. You run the simulation of mold compensation with or without feeders and gatings, but the feeders should not be compensated, or they can of course be run with the compensation, but it's not something that should be used later on. So they can influence the result, but they are not interested to use for the compensated shape at all. Then we have the simulation of solidification down to 50, it should be, 5 is wrong, 50 to 100 degrees, or as near as room temperature as possible. And then you start the stress simulation and let it finish. With the data we have talked about, if you are going to use the full contact task or the contact task, that is something that you have to decide. In the browser, we take the last step of displacement and send it out with an acceleration of -1. We have, for the acceleration factors, we have -1, we have 0, and we have 1. 0 is the nominal, that is the starting point. 1 is the displaced part when we have done the stress calculation. And -1 is, of course, the opposite of the +1 part. So it's on the other side. So we are trying to reverse engineering from +1 to -1 to end up with 0. And we are going to use this STL file for the pattern or the verifying simulation in order to see that the simulation now gives the correct shape and dimensions. In the beginning, of course, you would like to verify that by the simulation. But hopefully, in the long run, we are going to be able to use this kind of pattern or die prediction in order to simulate how the pattern and the die should be manufactured. So here's a schematic of the procedure. You take the final casting dimensions and the 3D final casting dimensions. Go to 3D import, set up the simulation. Set up the 3D file, I would say. Set up the simulation, define shakeout time and conditions. Shakeout, don't forget that, because if you are changing the conditions of the surrounding area, like for example, if you are taking away the mode, then there is potential for free deformation. Then you don't have any full contact task or contact task that restricts the deformation, and then you will have less stresses and more deformation or displacement. Then you go to solidification or flow and solid. Of course, you can run it with flow and solid as well if you want to. Run the simulation down to plus 50 or 100 or as near to your room temperature you have set at the moment here as possible, but at least somewhere in this range. Then you go to NovaStress, load the simulation, go to the browser and run the simulation there. Go to the browser and then you do the reverse and set -1. Export that STL file, and then you can go to the 3D import or CAD system for pattern production, or 3D import for simulation or CAD system for pattern production. So that is how it's going to be done. I have been working with 3 different files. They are without gating system in this case and feeders, but we will see what happens. So the first one is you can see a little bit on this is also exaggerated, as you can see 10 times. You can see that you get some movement of the part and change in shape and so on. It changes shape and it changes dimension. So it will be shrinking on the length and so on, and the width and height. So here's the nominal part. I have done it like this. I have exported the nominal part, displaced part, and the 3D compensated part after the simulation. So I have done all parts here in order to understand. So this is the first simulation, the 2 first here, and this is the second simulation when we have sent out the -1 part. So if we look here, we can see that the blue part and the red part is not really coinciding, and that's because the red part has moved or shrunk and moved in some different directions. You can see, for example, here we see the blue part here on the side here, and I see it here, that's blue part. That means that the red part has gone inside the blue part here, which is of course pretty normal. It's not done that everywhere, as you can see, but on some places it has. That is of course not what we want. That means that we have got the deviation from the nominal part, which could be correct if you have done a really, really good job with your nominal part, which is the starting point for the stress calculation. But here we have started with the real part, the casting part we want in the end. So instead, we have this, where we can see the 3D compensating part, which is then compared with the nominal part. So we have the -1 part simulated, so to say. So it's not the -1, but it's a simulated part here after the second stress simulation. You can see it coinciding perfectly here. This is really, really good, I would say. I don't get this good on everything, but here we have got a really, really good match. We'll see all the other ones also. Then we have the second part here. And this is actually from the start, the high pressure die casting part. It's also accelerated 10 times. It's quite a funny part, actually. We have shown it, I think, on some exhibitions. It's from a Swedish foundry. It's a Swedish company that designed this part. I don't think they decided in the view that it should actually be this shape, because this kind of bending is completely built into the part. We have tried, I think I tried 10 different ways to compensate for this distortion. It was impossible. In the end, they had to do it with manually, which is not, of course, correct, because then you can initiate cracks and so on. But it's interesting because here we can see that we have been able to match it perfectly. I think we have had a presentation about this before, and we had a match of within tenths of millimeter, more or less, that we got the right size. And actually on this exhibition, I can't remember if it was Eurogus or if it was GIFA I showed it on. We had a part that I had 3D printed out, smaller in dimension, but still. And it had exactly the same behavior if you put it on the table as the real part, meaning that it was not lying flat on the table at all. And here we have the same thing here. We have the nominal part, which is the blue one. Then we have the the yellow one, which you can see then directly that it's showing a strange behavior here. And if we have done this with the compensation then, with the -1 part simulation, we get this instead. It's not, as I said, it's not a perfect match, but you can see a big difference here, because now we are starting to get within the same area. If the company had done it with this kind of compensated part, it didn't matter if we have had this distortion, because it would have ended up with the right dimension anyway. In this case, the part was designed with the distortion behavior, and then we have to compensate for that distortion behavior. That would be possible to do. Of course, if the distortion is too much, it could be a problem to design the tool, because it could be that you can't actually, there will be a kind of a undercut or something like that. So that would be a problem in that case. But that is something you have to look at, of course. So a summary of this study is that you can get the good result. You can found a good result if you are using this nominal dimensions, and then the final simulation result based on the -1 STL file. So you can see directly here. Next step, of course, is that we are going to do this in real life. And actually, we have a project now. This is a investment casting foundry. They are, of course, relying a lot on their accuracy and tolerances. And we are going to do this in this project together with the RISE, GICA, and the TPC in order to really predict this. And we are going to 3D print the part we have been kind of compensating or predicting. And then we are going to study the results. I think that one thing we have done wrong historically is that we have been using the wrong starting point. It has not been the nominal dimensions, and then you cannot compensate. If you are starting with the pattern or the mold cavity, then of course you can verify what happens if you are having that kind of results. But you can never go to this really good die prediction or pattern prediction if you are not starting with the nominal dimensions of the part. And as I said, in-gates and feeders are not interesting to compensate. They should be used for other purposes, so they should not have a compensation. But you can use them, of course, in order to get a better calculation. But you have to combine them, as I said, with a nominal casting part. And in most cases, we can use the solidification simulation. It's enough. There are some rare cases where you have very thin mold casting parts, short solidification times. Then I would suggest to use the full. And for high pressure die casting, definitely you should use the full, of course. Different file exports are controlled by the exaggeration factor. So 0 is nominal part, +1 is the base part after first best calculation, -1 is then the compensated part that should be exported as an STL file. And of course, when you have done the second simulation, this is the +1 that you should look at, nothing else. The +1 is the result of the stress calculation. So very important to remember.
So the big potential with this method is that you can use it in order to make the correct compensation of the pattern or the mold in order to get the right dimensions and also the right shape of the casting parts directly without doing any compensations afterwards or making any changes to the pattern or the mold prior to you have done the first iteration of the mold or the first machining of the mold or the pattern. And that saves money and time a lot as we see it. And we can see a great potential for all types of casting methods, but especially the ones that you have high accuracy, you need to have high accuracy, where it is precision casting, so to say. There you have a big potential for the future, like for high pressure die casting and for lost wax method or investment casting as it's also called. But I would say that all types of castings can be more accurate in the future and also more correct in shape. so you don't have to do corrections. And also, I think in many times you are also making like adding material to the casting part in order to be on the safe side that your casting part can be machined correctly, because you might otherwise have lack of material on some places, and that should be avoided in the future as we see it. So the method is really, really good in order to compensate for this kind of things, instead of just adding a percentage value which is not correct.
In the next NCTV episode, we will guide you in taking the perfect sample for your metallurgical process control system and why it's so important. Thanks for watching, and see you next time.